This is your standard equation for the ellipse. X minus x naught quantity squared over a squared plus y minus y naught quantity squared over b squared is equal to 1. And for this case, they're saying a is bigger than b, but you can also have that switch where b is bigger than a. And then there's going to be a slight change in your graph, but essentially it'll look like an ellipse.
Does that make the difference of a horizontal
Yeah.
ellipse versus a vertical?
Yeah. It makes a difference between whether your ellipse looks like it's elongated horizontally or vertically. So graphically, where A is bigger than B, in this case your ellipse would look something like this. Now I put these look like x and y axes, and normally it would be your x and y axis, but let's not call these x and y axis. So let's say this isn't necessarily the x and y axis. And what I'll do is I'll change the center of the ellipse to be the center of the ellipse x naught, y naught. So the center of the ellipse can be anywhere in your two-dimensional space. It's easiest when it's at 0, but it's not necessarily going to be the case, so we have to make sure we adjust for that. The foci of the ellipse are x naught minus c comma y naught. So if this here is your x naught and this here is your y naught, then there's going to be some distance c. I'll use a different color here. Where the distance is measured from the center point to some value called the foci, focus point. And then the same distance on the other side will be your other focus. Now, since A is bigger than B in this case, your A is the value that's below the x squared value. And so along the x-axis, the horizontal axis, you're going to move from x naught to this point. X naught plus A. And then the y value is whatever the y value that is, which is y naught. What that's saying is that the distance from the center point to the edge of the ellipse is your A value. And same goes on the other side. So this point over here would be x naught minus A instead of x naught plus A. It'll be x naught minus A, and the y value is still going to be y naught. So this horizontal axis, which is not the x-axis, not necessarily the x-axis, but it's some parallel to the x-axis. Since A is the larger value over B, this is going to be called your major axis, because that's the one that has a longer side of the ellipse, which means the other axis is called your minor axis. and this has a distance of b from the center point to the edge of the ellipse. Which means we can identify the edge of the ellipse with an x value of x naught and a y value of y naught plus the offset, the distance of your minor axis, which is b. Similarly down below. So the only other important thing to remember here is for us to be able to find the focus point, we need the value of c, and c in this case is going to be this quantity, the square root of a squared minus b squared. Now, I kind of didn't talk about the ellipse from a graphical point of view, but the definition of the ellipse is kind of set up according to distances again, just like the distances for the parabola. Remember, the parabola was defined as all the points that's equidistant to from the focus to the directrix. And here, there's some similar definition where the ellipse are going to be all the points so that the point from the focus, let's call this F1 and F2, focus point 1 and focus point 2. That means the total distance from F1 to any point on the ellipse and F2 and that same point on the ellipse is going to be the same. So imagine adding up this distance over here. That will have the same amount of distance if you go anywhere else on the ellipse. So this distance plus this distance I don't know how we should call it. Let's say the 1 tag plus the 2 tags. It'll be the same as the 3 tags plus the 4 tags. It would be the same if you add these two distances. So this distance here, these two line segments, the distance of those two line segments is the same as the distance of these two line segments. And then if I pick any other point on the ellipse, the distance of these two line segments that connect that point to the focus, to each of the foci, will be the same also. If you Google an ellipse, you might run into a picture of 2 nails on a board. Seeing something like that? You got 2 nails on the board and then a string attached to them, to these 2 nails. And then you take your pencil and then you stretch that out and then you draw what would be an ellipse, because you're kind of restricted to the length of that string that's connecting those 2 nails. Okay? So that's another way to try to visualize this. One of the things that's going to be important for us is trying to distinguish between a parabola versus an ellipse versus the other conic section graphs that we're going to study. And so between the ellipse and the parabola that we saw last time, what can you say is a major difference between these two graphs?
Well, a parabola is open-ended, whereas ellipse.
Okay. the graph itself, the ellipse is an enclosed thing, and then the parabola is open. How about the equations? I mean, this is the standard equation, and the ellipses that you guys will run into may not look like this at first, but you have some algebra to do to make it look like this. But if you were to look at a couple of equations, how would you know if something is a parabola versus something is an ellipse? Yeah?
You make the assumption that the ellipse is parabola actually like half symmetrically.
Not quite. No, not quite. But the equation, how about the equation? So for an ellipse, both the x and the y is squared. For a parabola, if you look back at your notes, you'll see one of the variables is squared, but the other one is not. Okay? So that's what you want to watch out for. So parabola, one of the variables is squared, the other is not. For an ellipse, both of them are squared. Okay, we'll try to run that down at the end of, towards the end of class. Like once we have our, I guess we have a couple more shapes that we're going to study, conic section shapes. All right, let's take a look at the assignment. And I have to change this because I don't want to just do your assignment for you. I know the numbers are a little bit different and changed, but I think at some point we need to. I'm just going to take random problems from other places. And they don't have any good problems here. Let's see. All right, they don't have any problems that I want to do right now, but we'll see if we can come up with another one. Here's one that I'm looking at on a different sheet of paper here. Let's say you had an equation that looks like this: x squared plus y squared minus 2x minus 4y minus 4 equals 0. So we only know the difference between an ellipse and a parabola at this point. Can you tell me why this is not a parabola? Because both the x and the y squared. Remember not just to look at the y squared, because if the x wasn't squared, then this would still be a parabola, except it will go sideways. Okay? So this is an ellipse. If you can convince yourself that this is an ellipse, then we're good to go. What we want to do to make it look like an ellipse is we want to make it look like this equation right here. So we want to complete a square, maybe 2, and we want the right-hand side to be equal to 1. Okay? So that's our task. So in order to complete the square, what I want to do is I want to collect all the variables together, squared and non-squared, and then somehow complete the square that way. So we have an x squared minus 2x, and let me wrap some parentheses around that because I'll deal with that in a minute. We got y squared and 4y minus, leave some space there. And then let's bring this term over to the other side already, so the negative 4 becomes a plus 4 on the other side. So we want to collect all the x's, all the variables together, and then anything that doesn't have any of the variables, let's put on the other side, and we'll deal with that in a minute. So let's complete the square, and here in completing the square, I want to add the appropriate value, and when I add the appropriate value, I want to make sure I subtract the appropriate value as well. So I add within here, I take the middle term. We've done this before. You take the middle term, which is 2. Not the x, just the 2. You take 2, you divide it by 2, and then you square it. So that's 1. I added a 1 in here, so I need to add, I guess I'd not subtract, but since this is balancing the equation, I want to add the same 1 on the other side. And if you go through the same process, you'll add a 4 to the y component, so I'll add the 4 on the other side. So with a complete square, we have x minus the same sign, and the square root of 1 is 1, plus with the y's, you have the y, the same sign as the middle term, square root of 4 is 2. And then you can double check by foiling this out to make sure that you get the same values. And then 4, 4, and 1 is 9, so I have that nice and easy number on the other side. Oh man, this isn't an ellipse. Well, at least you'll know what a circle looks like. Where's my ellipse equation example? All right. Oh, my idea was dividing by 9 to get 1 on the other side. Let me do that just to show you, but you'll see that what happens when you divide by 9 on both sides, you get x minus 1 squared. And I'm going to rewrite 9 as 3 squared. And then we have y minus 2 squared over divide by 9 here also will give us 3 squared is equal to 1. So because these are the same, if you imagine your ellipse having the same distance in the x and in the y, it looks just like a circle, and that's what it is. So this is a circle. So let's say the general equation for the circle kind of looks like x minus x naught squared plus y minus y naught squared is equal to r squared. So the radius in this case is 3 in our example. And if you were to graph this, you would go to 1, 2, 1, 2 as your center point, and then you have a radius of 3, 1, 2, 3, 1, 2, 3. All right, so it kind of makes sense that an ellipse kind of works the same way as a circle, except the two numbers that would make the ellipse kind of an ellipse would be the same, in which case it would make it into a circle. All right, I didn't mean to do that problem. Let's try another one where we're actually looking at an ellipse. Just in case it wasn't clear, for the equation of the circle, the x naught comma y naught is your center point, and then your r is your radius. All right, sorry, let's go back to an example of an ellipse. I'm going to squeeze this in over here. And here's the one I should have looked at. lot of times when things are written where it's equal to 0, it's kind of called standard form. So our equation, x squared minus 4x plus 4y squared plus 24y plus 24 is equal to 0. This is not a parabola because both the x squareds and the y squared, or both the x and the y are squared, or there's some value of x and y that's being squared, variable. And I would say it's not a circle because the coefficients of x and y are different. So we'll talk about how that coefficient comes into play when we start completing the square. So let's complete the square. And for completing the square, again, we want all the x's together and all the y's together. And then things that don't have an x and y can go on the other side. So we have x squared minus 4x. This part I think will be easy to complete. But now we have a 4y squared plus 24y. And this one I'm going to work with a little bit more before I continue completing the square. So right now our other side is a negative. So hopefully that'll become a positive. Otherwise this thing might not make sense. All right. We could do this now or we could do this in the next step, but I wanted to include an extra step here so that we can focus on when you have a coefficient and you're trying to complete the square. And when you have a coefficient, there's several ways to approach this. The way I'm going to do it is I'm going to factor out the coefficient out of the two terms that involve a y, so that the leading term here is just 1 in the parentheses. And that means I took out a 4 from 24, so I think that's a 6, right? So now let's figure out what to add to both sides to complete our square. Like I said, the first one wasn't too bad. It's pretty easy. You got 4. Half of 4 is 2, and you square that, you get 4 again. So we're adding 4 to both sides. Now, in completing the square here, half of 6 is 3, and then 3 squared is 9, right? Now, unfortunately, you're not just adding 9 here, because you added 9 and you passed it through this parentheses, which had a 4 in it. So what are you actually adding? You're adding 9 times 4. Right? Which is 36. 36? 36. So you're really adding 9 times 4 to both sides of the equation. All right. Now let's see if we can finish this off. We have completed square, x minus 2, quantity squared. We have a coefficient 4 outside. Y minus square root of 9 is 3, plus quantity squared, and this is equal to 36 plus 4, and then you subtract 24, 16. Okay. It almost looks like the ellipse, except we want to divide out by 16 to get a 1 on the right-hand side. So if we divide by 16, you get x minus 2 squared divided by 16. Let's call it 4 squared so that we can easily identify the major or minor axis. I don't know what this is going to be. Y plus 3 squared. And we'll do a couple of steps here at once. We have 4, and then we're dividing out a 16, so that would cancel, and we would have 4 in the bottom. Is that correct? So we got 2 squared in the bottom, and then by dividing out by 16, the right-hand side becomes a 1. So here it looks exactly like the equation that we had. Before we draw it, we can identify all kinds of things. We can identify the center point. What is the center point for this graph? Two, -3. We got the center point. We have, the focus is a little bit more complicated. Let's see. Which one is the major axis? The x-axis, the variable, or the coefficient, not the coefficient, but the denominator under the x is larger. So I'll say x-axis, but it's really x is equal to 2, right? Or y is equal to -3, whatever. How should we write this? How did they write it? How did they describe it? They described it using vertices are located at x0 plus or minus a, comma y0. So let's write it like that. So x0 is 2. 2 plus or minus a, that's 4, comma y0 is 3. So 2 plus 4 is 6, right? So that is 6, comma 3. And then 2 minus 4 is -2. -2, comma 3. So that's your major axis. Is it -3? -3? And then your minor axis, we'll try to describe it the same way. So your minor axis is 2. It's x0, and then comma y0, which is -3, plus or minus the b value, which is 2. So these form your, I guess they call it vertices, the major vertex vertices and the minor vertices. So we have 2, comma -1, 2, comma -5. So this will help you actually draw the ellipse. The focus, the foci, are not part of the drawing of the ellipse, but it would just be good to find out what they are. So let's find our foci. And for that we need a C. And then I think it's the difference squared, or is it the sum squared? Difference. So let's take A, which is 2, or 4. 4 squared minus, and then 2 squared. What is this? This is square root of 12. Let's get a decimal approximation for this. I think it's 3 point something. 3.46, just to give us an idea of how the graph would look like. So A is the denominator of x, y is the denominator of, or B is the denominator of y. So this kind of makes sense. Our major axis goes from the middle to 4 units to the left and to the right. And this is 3.46, which is a little bit short of the 4 units to the left and to the right. So I think we might be ready to draw this. Let's draw it with respect to the origin. Let's say 2, -3, so. Let's put 1, 2, 1, 2, 1, 2, 3. Let's put this as our center point. And so that's the center. We have the major axis is 6, comma -3. This is 2, 3, 4, 5, 6, comma -3. -2, comma -3. So these two are like the vertices. And along the minor axis, we're at 2, comma -1, and 2, comma -5. 1, 2, 3, 4, 5. So let's just put those together. And then the foci go along the major axis. So along the major axis over here, we have a distance from the center. This is 4 units from the center to the edge. So 3.46 would be somewhere over here. And subtract 3.46 would be somewhere over here. So these two over here are the foci. And that's your ellipse. Okay? Any questions? There are no points here identified. Let's identify this as 2, comma -3. Whoa. Then identify the distance here as 2 and the distance here as 4. Okay? Any questions? So in this example, and the one we did before, the circle, and in the one we did last class, we looked at an equation, and then we found out that it's a parabola or an ellipse or a circle, and then we completed the square and did all that stuff. In some of the homework problems that you'll have, they'll give you information about an ellipse, and then they expect you to find the equation for it. So let's take a look at a possible homework problem where they do that. This one, for example, consider the following. Find the equation of the ellipse and its foci. So let's see if we can do this problem. And what we're going to need to do is essentially go backwards from what we're used to doing, where we have an equation and we complete the square and identify different things. This time, we're going to go backwards a little bit. So from a graphical point of view, what we can identify easily is the center of the ellipse. Then we can identify some distances, the major axis distance and the minor axis distance. And I think that's all we need. Once we figure that out, we can identify your A and your B and then focus points. So what is the center? Looks like it's 1, 2. And the major axis distance and I'm going to go ahead and call this A. And you said it was 2, yeah? And the minor axis is going to be 1 unit. Well, I think I have everything for the ellipse. Right? So the equation, if you remember, it's going to be x minus x naught squared over a squared plus y minus y naught squared over b squared is equal to 1. So your a, your x naught is 1, your y naught is 2, your a is 2, your b is 1. So that's your equation. Okay? Now the foci is an actual point. Actually, it's a couple of points that's based on finding a value c, which you can get from A and B. So to get the foci, we need c, a squared minus b squared. And if b was bigger, then you switch that around. So we have 4 minus 1, which is square root of 3. And that c is a distance from the middle to your focus point. And it goes both ways, left and to the right. So to actually identify these points, I have to start from the center point, right? So from the center point 1, and then I move by a distance of 3 to the left and to the right. So to the left, I'm subtracting square root of 3. And then what's the y value? The y value remains the same, which is 2. And then I just found the left side, so if I want to find the right side, instead of subtracting square root of 3, I'm going to add square root of 3. So that's going to be my other point. Yeah, you're going to switch b and a because you can't have a negative under a square root. And that just means your ellipse now will be elongated vertically instead of horizontally. Okay, should we check? This is correct. All right. So all the examples that we've done have been an ellipse stretched horizontally, but you can imagine the slight differences when it's stretched vertically, and you can work that out yourselves. I don't know what the book does. I think the book actually switches the A and the B, but I tend to like to keep A under the X and B under the Y, and then you can decide from there which one is bigger, which way your ellipse is going to go. All right, let's move to our next Our next conic section shape is the hyperbola. So the hyperbola looks at two focus points again, two foci, and then instead of adding, you know how with the ellipse we have that string and you add the difference, or you add the value of the string from the focus points to the point on the ellipse, it's going to be the same all over. Here, it's harder to visualize, but we're looking at the difference between the 2 points. So what is the difference between, in terms of the equation, what is the difference between the equation of a hyperbola versus the equation of an ellipse? There's going to be a negative sign in the hyperbola. Now, whether the x is negative or the y is negative is going to depend on how this is going to look like. And we'll take a look at a few I like to think of it as common sense ideas that would tell you whether something's going upward or sideways. So let's get this kind of sketched out the way we did the other one. So again, you have some new axes that it's not necessarily your x or your y axis, but it's based on your center point. So your center point is x naught comma y naught. And you have your foci. I guess in this case we're going to open sideways first. Your foci is along a major axis, or an axis, not necessarily major. And what we're looking at, the shape of the parabola or the hyperbola, would look like this, more or less. So this is the logical part that I want you to think about. You have a quantity x minus x naught and you're squaring it over a, and then y minus y naught and you're squaring that over b squared. And this is supposed to equal a 1, which means this is supposed to be positive, right? So what I want you to think about is if the top quantity in x or the y is equal to 0. Think about if the top quantity of the x or the y is equal to 0. So what I mean by that is that if I want to try to plot something with an x naught in it, this is x naught comma some y value. I don't know what the y value is. But if I want to try to plot that, what I would get here is that if I put the x naught in for x, this is the top part is going to be 0. And then this may or may not be 0. Let's just say it's non-zero. And then it has a negative in front of it. And this is supposed to equal positive 1. So when you do something like that, this is not going to work for us, which means your graph is not going to pass through this vertical line. Does that make sense? That logic? If you turn it around the other way, if you put a value over here like some x value, which I'm not sure yet, comma y naught. So that would make this y minus y naught equal to 0. And that would make the x value not equal to 0. So the fact that this goes away means the negative part of this goes away, and then I have something that could equal a 1. And if this was part of the graph, how would I make that something equal to 1? So how would I find this question mark if I want this to equal a 1? So I have x minus x naught quantity squared over a squared, and I made the other one disappear because I put y naught in for y. And so how do I solve for my x value here? I get x is equal to, I'll bring the a over to the other side, a squared over to the other side. I would need to take the square root, so that's just a, and then I would add x naught. So if you do that to the other side, or this whole idea about taking the square root produces a plus and minus side of things. If you do that to the other side, you'll get the other vertex point for your hyperbola. So that's how you can try to think about it logically when you're trying to figure out whether this is opening inward or outward, or I'm sorry, whether it's opening sideways or up and down. You can think about which part of the hyperbola you're going to draw. All right, the last thing about this is that there are some asymptotes. There's a line the line passes through the point x naught comma y naught, and it has slope, well, either b minus a or negative b minus a. What you can do is that if you can draw those lines, you can imagine the hyperbola using those lines as a guide and as an asymptote, where it would get closer and closer to those lines. Okay? So you might have known how to find these, maybe not necessarily these lines, but you might know how to find these asymptotes from before. Any ideas? From pre-calculus maybe? All right, well, the a goes with the x, so if I go an a distance here, we've done that before, right? A distance there, a distance over here. And then the other axis, the b goes under the y, so if you move some y distance, b distance along the y. What you could do is you can make a box. Out of that. And that box, well, this is supposed to go through that corner. And the box will have those corners as the guide for your lines. Have you seen that before? Okay. So that's another way to get it. Just by looking at the A and the B, make that box out of this and then draw those lines along the corner, and these lines would be your guide to your hyperbola. Formally, you can find that equation using this. It's a slope, and then x minus x naught plus y naught on the outside. Okay? Suppose we should do an example. Let's try an example. We got 6x squared minus 4y squared plus 8y minus 24x plus 16 is equal to 0. So first of all, you convince yourself that it's not a parabola because both variables are squared. Somewhere along the line, both variables are squared. It's not a parabola. Now, you also have to convince yourself that it's not an ellipse because one of the squared terms is positive, the other squared term is negative. So it's not an ellipse. So now, you know that's hyperbola. All right, let's break it up like we've been doing before. And I'm going to go ahead and factor out a negative 4 when I break up the y. Okay, so I'm going to do a couple steps here. I'm going to factor out a 6 out of the x's. So I'm essentially skipping a step. And then for the y's, I'm going to take out a negative 4. So negative 4 out of this would be positive y squared. Negative 4 out of positive 8 would give me negative 2y. And then I'll go ahead and bring the 16 over to the other side. Okay. Now we're going to add some stuff to both sides to make it a perfect square, to make each of these terms a perfect square. So I need to add a 4. So half of 4 is 2. Square that, you get 4. But what am I actually adding here? 4 times 6 is 24. Half of 2 is 1. 1 squared is 1. What am I actually adding? Negative 4. Negative 4 times 1. All right, let's go ahead and complete the square. We get 6x minus 2 squared minus 4 y minus 1 squared is equal to 4. And let's just divide out by 4 so that we have a 1 on the other side. That will help us identify the a and the b. So I have x minus 2 squared. I divide this by 4. So think about 6 over 4, and then you want to force that to go in the bottom. Right? So it becomes 4 over 6. So you can leave it like that, or you can think about this as something that needs to be squared because I need to identify this as something being squared. So it goes in the bottom as 4 over 6 because this is 6 divided by 4. It goes in the bottom as 4 over 6, and then I want to look at it as something that's squared so that I can easily identify my a. And so 4, 6 in the denominator is the same thing as the square root of 4, 6 quantity squared. And then 4 over 4 is just 1, so that'll leave us without a coefficient. Or you can think about your b as being 1 squared. Okay. Now let's get an approximation for square root of 4/6. I guess that's 2/3, isn't it? What's the square root of 2/3? 0.82. Okay. B is equal to 1. So we should be ready to get some sort of draft of how this might look like. Where's my center? My center is at 2, 1, 2, 1. So my A is along the X. I want to go 0.8 units. Maybe I need to write this. Maybe I need to do this a little bit bigger. 1, 2, 1, 2, 1. Now along the x-axis, that's that number under the x. I'm moving about 0.82 units to the left and to the right. So that's going to end up being my vertex. Because the x is the one that's positive, so I'm going to move along the x. This is going to be a sideways parabola. And my b goes up 1. And what I could do is I can draw a box. And then draw lines passing through the diagonal. And then now, we kind of figured it out already, but just to make sure, we are going sideways, right? Because the x is the one that's positive. So from your vertex on the side, you're going to draw a hyperbola. Okay? Now, a couple of things that you can find, you can do this on your own. You can find the foci, which is going to be on the outside of the hyperbola. You can also find the equations of these lines. We have formulas for that from the previous page. And so all it is once you've written your equation into your standard form, then you can identify the A's, the B's, the C's. You can find the equation of the line, the two lines that are involved. And it's just going to be plus and minus the slope. It's going to be the same slope, except one has a positive slope, one has a negative slope, and it passes through this center point. All right? Okay, so hopefully that's enough information for the conic sections. And then what we're going to do is we're going to tie in the conic sections with polar coordinates next time. And then that'll allow us to do some calculus.